템플릿에 보면 여기 몇 페이지가 안 나와 있네요. 뭐 이런 엊그제 세미나 했던 자료입니다. 자료는 아니고 아무튼 거기 팜플릿 보면 중간에 이런 페이지가 있어요. 발표하신 분들 내용하고 그 다음에 뭐 랩시 전문 솔루션에서 그것도 있고 그 페이지 보시면 OPUS 10, SIMLOX, CATLOC 이렇게 해서 이고, 커넥트, 인사이트 이렇게 세 개가 이렇게 추가적으로 있거든요. 그거 잠깐 말씀을 드릴게요. 왜 그러냐면 사실 중요한 것들입니다. 잘 아시겠지만 데이터라는 개념이 10년 전, 20년 전의 데이터하고 전혀 틀려요. 지금 데이터들은. 그래서 그런 데이터 스트럭처가 군수 분야에도 바뀌어가지고 SSD라는 게 이제 나오고 뭐 그런 쪽으로 이제 가려고 하고 있다 이렇게 생각하시면 될 것 같고 그런 경향에 맞춰가지고 실제 LSAR 데이터들을 어떻게 효율적으로 빨리 응용을 할 수 있을지에 대해서 고민을 하다가 아마 만들어낸 게 커넥트라는 게 있습니다. 밑에서 두 번째. 그래서 아마 세미나 때 잠깐 보여준 것 같긴 한데 요네스가 잠깐 보여줬던 것 같기도 하고요. 제가 봤을 때. 그 다음에 그러한 데이터 스트럭처를 아무튼 우리가 준비를 해야 된다. 해야 되는 이유는 간단합니다. 우리 같은 경우 주로 수출에 목을 메고 있고 무기체계에 대해서 거꾸로 우리 내부적으로도 옛날에 데이터 프레임하고 데이터 스트럭처가 바뀌어야 될 때가 지금 됐다라는 얘기예요. 뭐 우리 솔로몬이 됐건 델리스가 됐건 우리 1388 2B가 됐건 뭐가 됐건 아무튼 잘 하고 있는데 그 방식대로 계속하는 거는 좀 한계가 있지 않냐 이제 이런 상황이고요. 연구를 한번 해주시면 되고 그 다음에 쓸데없는 얘기 잠깐 할게요. 우리가 지금 어제 오늘 교육받는 내용들은 크게 한마디로 얘기하면 우리한테 주어진 문제를 푼다라는 뜻이거든요. 문제를 해결하고자 하는 겁니다. 우리한테 주어진 거는 이제 군수 분야에 우리의 문제를 이제 해결하는 방법인데 그거에 관해서 이틀 동안 얘기를 하는 건데 우리 초등학교, 대학원을 다니면서 우리가 여태까지 배웠던 과학적인 방법론이라는 건 두 가지밖에 없습니다. 사실 우리가 늘 거의 편중에서 배웠죠. 학교 다닐 때 디터미니스틱한 방법을 주로 많이 배웁니다. 우리 같은 경우가 특히 우리나라 교육 체계의 문제일 수도 있어요. 그래서 대개 경우 정답이 하나로 딱 떨어지는 거는 되게 사람들이 선호합니다. 왜 그러냐면 우리가 그렇게 트레이닝을 받아가지고 아무튼 그래서 그러한 방법을 이용해가지고 어떤 문제를 해결하는 방법이 뭐 어제 했던 OPUS 10이라고 생각하시면 돼요. 그래서 뭐 이 친구도 얘기했죠. 디터미니스틱한 방법을 쓰고 그러다 보니까 나이스한 수학 모델이 있을 수가 있다라는 얘기고요. 근데 현실은 꼭 그런 건 아니죠. 현실이 그랬으면 참 편한데 우리도 일하기도 편하고 언제 고장날지가 금방 예측이 되고 언제 스페어가 필요할지 금방 예측이 되죠. 그런 방법들이 잘 적용이 된다. 근데 현실은 그렇지가 않습니다. 대개 경우 두 개가 이제 혼재돼서 나온다는 얘기죠. 그런 디터미니스틱한 방법도 필요하지만 때로는 우리가 싫어하는 프로바빌리스틱한 방법들이 또 필요할 때도 있습니다. 실제로. 그래서 이 두 가지 방법들을 적절하게 믹스를 해서 우리의 문제를 해결하는 건데 그 이외의 방법은 사실 없어요. 우리가 배웠던 것들 중에. 앞으로 AI가 어떤 것들을 만들어낼지 모르겠는데 아무튼 현재 우리 수준에서 할 수 있는 방법들은 두 가지 방법이 있고 모두 아마 그런 프로바빌리스틱한 아이디어를 이용해가지고 그거를 MNS에다가 적용을 하고 그걸 이용해서 우리의 문제를 풀어내는 방법들 뭐 이런 것들에 대해서 아마 얘기가 될 것 같습니다. 그 다음에 제일 어려운 게 사실은 돈입니다. 돈 문제는 잘 아시겠지만 전문가가 있으면 안 돼요. 있을 수도 없습니다. 특히 우리 분야 같은 경우 군수 분야는 모든 사람들이 다 더군다나 모든 분야의 전문가들이 다 모여가지고 하는 분야다 보니까 내가 돈에 관련돼서는 최고야 이런 게 있을 수도 없다는 얘기예요. 그러다 보니까 우리가 코스트라는 또는 프라이스라는 여러 가지 관점에서 분석을 할 때 되게 어려움이 많습니다. 거꾸로 얘기해서 여러 분야의 전문가들이 모여가지고 돈에 대해서는 결정을 해줘야 돼요. 더군다나 이게 사이언스가 아닙니다. 돈에 관련된 내용은. 대개 경우 우리 현실에서 보면 정치도 들어가야 되고 매니지먼트도 들어가야 되고 뭐 여러 가지 내용들이 들어가야 돼요. 그러다 보니까 예를 들어서 캐틀락만 쓰면은 비용 문제가 해결된다? 웃긴 얘기죠. 말도 안 되는 소리죠, 사실. 그러다 보니까 우리가 과학적으로 접근했던 어제 했던 디터미니스틱한 방법, 그 다음에 오늘 하게 될 M&S 기법, 이 두 개를 믹스를 해서 리저너블한 모델을 이용하니까 이 정도 비용이 나온다. 그럼 이 모델에 대해서 또 다른 사람이 모여가지고 다시 비용에 대해서 얘기하고 이런 절차를 하는 거지. 어제 오늘 담당하는 어떤 교육이다 뭐 이런 거 아니라는 얘기입니다. 제 얘기는. 혹시 그럴까봐 종종 그런 경우가 많았었죠. 예전에 우리가 뭐 신뢰도 교육하면 이런 식으로 하면 신뢰도가 다 해결된다 이런 건 있을 수가 없다는 얘기입니다. 제 얘기는. 그래서 혹시 그런 오해를 하실까봐 그런 말씀 드린 거고요. 단 되게 중요한 거는 두 가지 방법을 해가지고 우리가 모델을 만들었을 때 이 모델을 이용해가지고 돈이라는 걸 쉽게 산출할 수 있는 방법을 제공하는 것까지는 가능합니다. 그래서 모델을 만들었고 모델이 문제가 없네? 오케이. 이런 모델에서 그럼 돈을 한번 빨리 뽑아봐. 이거까지는 가능합니다. 마찬가지예요. 오늘 하게 된 M&S를 막 여러 번 했습니다. 상당히 많이. 그랬을 때 많이 해가지고 우리가 추출해내는 건 결국 값이거든요. 평균적으로 어떤 경향을 보이는지, 그 다음에 그거에 해당하는 코스트가 어떻게 산출이 되야 되는지 이런 것까지는 쉽게 도구에서 제공하는 것들이고요. 그 결과에 대해서 이래라 저래라 맞다 틀리다 이런 얘기는 아니라 또 할 필요도 없고 이런 뜻입니다. 제 얘기는. 그래서 그런 문제들이 상당히 많이 여태까지 와 있었고 어제 잠깐 그 BA나 기타 등등 미국의 방산업체들에 간단하게 나왔습니다. 얘가 또 PBL 때문에 제가 사대주의자도 아니고 좋든 싫든 간에 미국이라는 나라가 이 분야에선 계속 앞서 왔고 또 그다음에 우리도 그 영향을 많이 받아서 군수지원 분석을 하고 있습니다. 그러다 보니까 그네들이 했던 여러 가지 내용들을 우리가 참고하는 경우가 많은데 그 친구들의 최근의 경향은 시스템이 상당히 복잡하고 커졌습니다. 돈도 많이 들어가고. 이러다 보니까 그거 자체에 대해서 모델링하는 것조차도 어렵다라고 지금 얘기합니다. 그렇지 않겠어요? 오퍼스텔로 돌리면 되는 거 아닌가? 뭐 그런 수준을 벗어난다는 얘기죠. 이제 지금 현재 상황 무기체계들이. 이러다 보니까 모델링을 그럼 어떻게 해야 되는데 상당히 어려운 문제. 그 다음에 불가능하다면 만약에 모델링하는 게 어떻게 우리가 접근을 해야 되냐 이런 문제에 이제 닥쳐있다 이렇게 생각하시면 되고 조만간 아마 우리도 그런 단계까지 가지 않을까 이렇게 생각이 됩니다. 그러다 보니까 주어진 문제를 수학적으로 나이스하게 모델링을 해가지고 아주 퍼펙트하게 어떤 답을 얻어내면 참 좋은데 그게 불가능하고 나이스한 수학적인 모델링이 불가능하다면 우리가 어떻게 모델링을 해야 되지? 그럼 우리가 부족한 부분에 대해서 어떤 또 다른 방법론이 있을까? 뭐 AI도 하나의 방법론이 될 수도 있죠, 사실은. 그래서 그러한 여러 가지 방법론을 이용해가지고 다시 한번 우리가 원하는 답을 한번 찾아보자라는 철학을 깔고 시작한 게 뭐다? 그 이보라고 써놨죠. 그게 이제 그런 도구라고 생각하시면 될 것 같습니다. 이건 아마 지금 퍼펙트하게 완성된 버전은 아니고 저도 이제 스웨덴에 가서 데모나 기타 뭐 이제 설명 자료만 제가 봤고요. 아직은 어쨌든 그런 식의 이제 방향으로 지금 바뀌어가고 있다라는 건 우리도 좀 인지를 하고 있어야 될 것 같습니다. 다시 얘기합니다. 너무 복잡해서 앞으로 세상은 우리가 모델링이 가능할까 이게 불가능할 수도 있다라는 걸 인지를 해야 됩니다. 그러다 보면 접근 방법은 간단합니다. 모델을 아주 심플하게 하는 방법이 있겠고 아니면 있는 그대로 보다 복잡한 현실을 가능한 한 많이 반영을 해가지고 우리가 모델링 하는데 부족한 부분은 있긴 하지만 그럼에도 불구하고 어떤 도구에 맡겨주면 그 도구가 우리가 부족한 모델링 부분을 해결할 수 있지 않을까라는 게 이제 최근의 경향이다 이렇게 생각하시면 될 것 같습니다. 그다음에 그 밑에 있는 인사이트 같은 경우는 사실은 도구는 아니고요. 그 예쁜 대시보드 이렇게 생각하시면 될 것 같습니다. 방대한 양의 자료를 가지고 분석을 하고 분석 결과들을 우리가 리뷰하는 것 자체도 여전히 힘든다. 워낙 많은 양의 결과들이 나오니까 그래서 그런 것들에 대해서 좀 심플하게 쉽게 그다음에 좀 예쁘게 이렇게 좀 결과들을 파악할 수 있는 대시보드다 이렇게 생각하시면 될 것 같아요. 그래서 오늘 시간이 얼마나 될지 모르겠지만 어제 했던 디터미니스틱한 방법을 이용해서 결과가 나오면 그걸 밸리데이션 시키는 하나의 방법으로 MLS를 이용하고 그 두 가지 결과에 대해서 비용 관점에서 어떻게 우리가 비용 요소들을 뽑아내야 되는지 오늘 해야 될 때가 두 가지일 것 같습니다. 그래서 심록스 잠깐 하고 그 다음에 캐틀락하고 연결해가지고 비용으로 이렇게 뽑아낼 수 있다. 그 다음에 어제 얘기했듯이 오퍼스텐에서 분석하는 건 LCC가 아니라고 그랬습니다. 단지 그냥 스페어나 또는 정비에 관련된 일반적인 비용을 뽑아주는 거고 더 정확한 LCC로 넘어가기 위해서는 캐틀락으로 어쨌든 넘어가야 됩니다. 그 다음에 여러 가지 코스트 드라이버들을 우리가 식별을 하고 그걸 통해서 계산할 수 있는 모델을 제공을 해줘야 되기 때문에 어쨌든 그런 이유로 캐틀락이 넘어간다는 얘기입니다. 그래서 그 두 가지 내용을 아마 보고 어쩌면 오늘은 조금 더 어제보다는 빨리 끝날 수도 있을 것 같아요. 간단하게 이렇게 하는 걸로 하겠습니다. 오케이.
Good morning. Good morning, everyone. Good to see you again. I hope you had a good evening yesterday and a good night's sleep, not dreaming too many nightmares about life cycle management. So, let me see here. Today, we're going to continue our exploration of the analytical capabilities of the OPUS suite within the analysis field in lifecycle management. Also today is focus more on the model and how to build up a model in OPUS suite and not so much on the theory of lifecycle management and things like that. We spent most of the day yesterday talking about OPUS 10 and the strategic decisions and analysis to be done in a deterministic model. Also, we saw how we could model the key elements in the logistics analysis. So, step by step, starting with the technical system and its properties, the logistics support organization and the operations, and how important all these three are together in order to get valid results. They can't be treated separately. They are the whole system together that needs to be in consideration when performing logistics analysis. I think that was a quite clear message from yesterday. Now, the good thing is that everything we learned yesterday when it comes to building up the model, we have benefits of today. Because when we are going to enter the world of simulation and analysis in time, in SIMLOX, it's exactly the same model as starting point from what we did yesterday. So both OPUS 10 and SIMLOX, they share the same input data. It is the same system that we are analyzing. We're just adding some more features and capabilities to it, at which the fact that we can use the time dimension also gives us some more possibilities, which we could not do in a deterministic model. So we won't have to redo that. Today we will build on what we did yesterday and continue the journey into the time dimension. So this is what we are going to do now in the morning, and after lunch we will continue and focus on life cycle cost modeling. So this will be a little bit to shift topic, not topic really, because this is the same, it's equally important. We yesterday talked a lot about costs and life support costs, and this is within the framework of the life. That's an important part of the life cycle cost, the life support cost. So the core notion here is, of course, how to model, how to build up cost model, and how to use the tool CATLOC for building up cost models. But the life cycle cost is an essential part of that, so we will have some theories about what is good practices when you are working with life cycle cost. So the purpose will be to talk about life cycle cost, how to set up a cost model in CATLOC, and what are the types of insights you can get from that, and also how you can use sensitivity analysis in order to study cost impact of changes and variations. And last but not least, we are going to talk about PBL and how we can use OPUS Suite as a good analytic platform for analyze the dynamics and mechanism within a PBL contract. So that's the plan, and as yesterday we have a lunch break around noon for 1 hour, and then 2 shorter breaks during the afternoon. And we will try to wrap it up not later than 17:40 to 20 minutes to 6. Could be earlier than that as well, depending on how fast I talk or model. So, any questions or thoughts from yesterday that you have come to think of? Oh, there's still chance to ask your questions later on today. Okay, we are going to talk about mission modeling and analysis in time, and this will also comprise of how to interpret results from the simulation, because that is sometimes a challenge to understand how results should be, what conclusions you can draw from the results. So that will also be part of this agenda item. And then we will also go into the tool itself and add incrementally some new aspects to the model and study what that does to the results. Yesterday, we put a lot of focus on studying performance versus cost. So how much does it cost to get to a certain performance? or what is the maximum performance you can get for a budget of support costs that you have. Opus 10 offers you this curve and it allows you to make sure that regardless what are your requirements or your budget, you can get optimal solution. Today, we are going to look at performance versus time. How is actually the performance varying with time? So, cost is not a part of this picture. So, of course, there is a cost involved here as well. But in the simulation study, we are focusing on the results, which are not the costs, but more from a performance and maintenance perspective. But if we consider that performance is something that is varying over time, other things also varies over time. So for example, systems operations. Yesterday we put a system operation average utilization over 1 year, but this is probably not the real case in the real world. We have varying operation over time. The resource availability is also something that can change over time. Transportation policy, failure rate, number of deployed systems, spare part stock allocations, task duration, systems accumulated age in operating time, mission profile, etc., etc. So once we open up this model to the time dimension, we get a lot of opportunities to change things and to study the dynamic response given that change. And this makes this field very interesting. So you could easily see by choosing a support strategy that has been dimensioned and optimized. First, you can test this strategy in the time dimension and see how robust it is against changes and variations over time. So therefore, we always recommend our users to use the tools Opus 10 and SIMLOX together in order to make sure that you get these two. They are completing the whole picture together. So if you get the results from Opus 10, that's perfect, that's good. It's perfect for dimensioning your support organization and get an understanding of your stock that you should buy. If you want to validate that from a more dynamic context, you should also test it in the time dimension to see if there are any bottlenecks somewhere down the line, or if it sustain the variations that may appear. So, if we talk in that the performance can vary over time and that we get an average value from our Opus 10 analysis, that could correspond in the time dimension a quite, quite varying value. So to understand when the performance is varying and why, that is the first step in order to understand what we can do about it. Can we accept it, that it's varying? Can we do something to mitigate it, etc.? I will try to do an extension here so I see. Like this is better, I think. Now I can see my notes as well here. So, this curve here describes the varying availability of a system. We can see that the system is either ready, available, or it is also on mission. This is the yellow field that appears down here. So we can see that we have a portion of our fleet. If you can consider that you have the fleet of systems on this side, you can see that the portion of the systems will from time to time be on operational activities, which is the yellow color here. And a portion of the systems are in a ready state. And if the fleet size equals the height of this diagram, we then see that at each point in time also we have unavailable systems. So if you consider this, if you take a snapshot at a certain time point in this diagram, you can consider that this is the status of my whole fleet. So if the number of systems equals here, let's say it's 100 systems or 10 systems, we understand that at any given point in time, we will have some systems on mission, some systems ready, and some systems unavailable. That's how to interpret this diagram. And of course, we want to know why the systems are unavailable. So, and this is something we can get from the analysis, from the simulation. We can see that a portion of systems that are unavailable are awaiting spare parts. Another portion of the systems are awaiting logistics resources. Some are just in administrative delay, just we are waiting for clearance, we're waiting for something else. Some systems are in active preventive maintenance, and some systems are in active unscheduled maintenance. Very colorful picture. But I would be a bit concerned in this case about these big dips of unavailability here. Anyway, an analysis like this gives us a good picture of what is the reason for our unavailability. And that's a good start if we want to address these issues and understand what we can do to mitigate them. But, yes, a question?
Yes, OPUS gives or report this kind of unavailability reason.
Yes.
Yes.
Absolutely. First of all, before continuing in SIMLOX and the simulation world, we need to talk about the difference between availability, readiness, and mission success. Sometimes you have, these are KPIs that often are subject to requirements. We must have 90% availability, or we need to have at least 95% mission success, etc. But you need to understand what that means in order to be able to verify if we can get there or not. Sometimes these figures are used a bit lightweighted because this sounds good with 90% availability, but we need to understand why do we need 90% availability. So let's take this small example here with the car. We have 10 vehicles like this. This is our fleet. One breaks down. This is availability 90%, right? If we have a mission requirement that says we must use 10 systems in operation, this is what the mission requires. We have 10 systems. So what is the probability of mission success if we have 90% availability? Zero. So availability is not the same as mission success. So if someone says, I need 90% availability, this is our requirement. Okay, but what do you want to do, really? What is your profile? We need more information to understand if this is satisfactory or not. One other thing is when you're talking about dimensioning the fleet. If I have this requirement on my fleet, if I have a requirement that, yes, I want 10 vehicles, we need that for our operating missions. Let's buy 10 vehicles. No, I would say, let's buy 12 or 13 vehicles, because we will always have one or maybe more vehicles unavailable. So a fleet of 10 vehicles will not be enough. So you need to buy some additional in order to have redundancy. This is something that seems quite self-evident, but sometimes people don't think like that. So now we have talked about availability and the reasons for unavailability, and we're talking about mission and mission requirements. So that leads us into try to look at how do we build up missions in Opus Suite. So a mission is something that has a certain duration. It can have a mission success point. By default, the success point is that when the whole mission is finished, then we have successfully completed the mission, but you can set that to, if 50% of the mission is completed, then you can consider it successful. That's up to you to decide. A mission requires a nominal number of systems for the mission. So we say, okay, this mission needs 4 vehicles. But we can also say that, okay, it's okay if one of the vehicles breaks down during the mission, it's okay. We can continue with 3. So this is the minimal number of systems that is required for the mission to be completed. We have a few types of mission, you can say, in SIMLOX, called mission patterns. We have a fixed mission, which is a scheduled mission with this duration length. It has definite start and stopping time, and if we must abort the mission for some reason, this is lost mission time. We're never going to get this again from this mission. This is lost and will be forever lost. Then we have a continuous mission profile. You can imagine, for example, a radar station that is operating 24/7. That's a typical continuous mission. Of course, we can have failure there as well, so we lose some mission time. But once the problem is fixed, the mission continues, and will do so. until we say that the mission is finished. Then we have extendable mission, which can also be interrupted due to failures, but the mission needs to be concluded. So once we have the capability back up and running again, the mission will continue. So it will be postponed, and you have to prolong the total calendar time in order to finish the mission. But the mission time will be the same, but you have just to extend it beyond the initial end point in order to finish it. So this is the definition of a mission. Now, once we have defined our missions, we would like to create some kind of operational profile from these missions. And an operational profile is a sequence of missions that you decide with a certain interval how often do these missions occur. And they can be how long and how structured in any way that you need or like. You don't have to structure them in a particular way. It's allowed to build up them. You can define a day, and you can define a week based on the days, and you can define a month based on the weeks, etc. So it gives you total freedom to design the mission profile, the operational profile that you want and need. And they don't have, if we have several missions of different types, you can define an operational profile which consists of a combination of various missions at various points in time, etc. And as with both support organization and technical system, start simple to build a simple operating profile, and as you gather more information and the analysis get more complex, you can build a more complex operational profile as well. So when you simulate, you typically start off, the operational profile will give you, this is the requested mission profile that that you should execute on. This is what we want to do. But during the simulation, we will find that some missions will be fulfilled and some missions will be lost. And of the fulfilled missions, we can get information about the achieved mission time, how many system hours have been spent on the missions, how many missions were successfully started, and how many missions were completed. But you also get the information about how much time you lost, how much requested system time you lost. And the difference between mission and system time is that, let's say that the mission is 1 hour, but we need 2 systems to complete the mission. That means that we have 2 system hours for that 1 mission hour. So we will track both the mission time and the requested system time. So if the mission allows you to continue with 1 system only, but preferably 2 systems, you will find that you have lost 1 system hour, completed 1 system hour, but the mission will be completed as well because it's allowed you to do it with 1 system. The lost missions, behind the lost missions are, of course, various reasons, like with the availability. One could be that you did not have enough systems to start the mission. There were simply not enough systems ready to when the mission was called, and the mission was aborted even before it started because we could not start it. But it could also be because we have systems that are waiting for different kinds of maintenance and is not available for that reason. So you can play both with the size of your fleet and with the maintenance response in order to make sure that you have enough systems to call your missions. We talked about operational profile, and this picture we had from yesterday in OPUS 10. We have an operational site, and in this case we have 2 units at this operational site which has systems deployed to them. And you typically assign an operational profile to a unit or an operational site. So yesterday we said that we assigned a certain number of operating hours per year to each site. Now we say instead we assign this operational profile to the site or to the unit to say execute on this operational profile. So this is the things that you need to add to your model in order to build up a mission profile instead of an average utilization. Define your missions and define your operational profiles and assign the profiles to the operative units. Questions so far?
오늘은 시간이 많습니다. 질문하셔도 됩니다. Okay.
Let's talk a little bit about how SIMLOX works and how to interpret the results. Since we are not calculating now deterministically with mathematical algorithms and formulas, which we did during the optimization in OPUS 10, now we are simulating, and SIMLOX is based on Monte Carlo simulation. That means that it's an event-driven simulation, and it means that things are happening as we play the scenario, and depending on what the events are happening, the course of action may go in different directions. But what is governing what is happening, it is the element of randomization, of chance. So it's like we are playing the scenario, we are rolling the dice for each given point in time. Will this failure occur with a certain probability? Let's roll the dice. No, it did not. We continue, we roll the dice for the next time period. Did the failure occur? Yes, it did. That was an event. What happens now? We are called for maintenance, etc. But as you can imagine, this is not a deterministic approach. It depends on the result of the dice that you throw. So, in order to get a confidence in the result for a simulation, we need to simulate multiple times. Only then we can get some kind of statistic validation of the results. So, and in SIMLOX we call these replications. And this is the result of one replication. When we played the scenario, the availability, the resulting availability of the fleet looks like this. But we don't want to make any decisions based on one replication, because we did not know, maybe we had a very bad luck this time. And we don't want to take decisions based on bad luck. Or maybe we got a too positive result, which is not according to what we can expect. So we need to play the scenario multiple times. We do the replication 2. We do the replication 3 and gather the result. You can see that the result is collected. And after 100 replications, we get the resulting curve, which is the average result over 100 replications. And now we can start to think, okay, it looks like this. We can be pretty sure that we will have a dip here and another dip in availability here, because over 100 applications, that has showed us it will occur. We have a statistical significant result. And we can also get some confidence measures out of the simulation, like the percentile, for example, here. And this means that in 90 of our 100 applications, this is the lower percentile, so that means that in 90 of the 100 applications, the availability was not lower than this line. It was above, on or above this line. So then we know that with 90% certainty, we will never be below this line. So that's some kind of confidence measure. If we collapse the time dimension now and want to calculate the average availability over the whole time, we get this result in SIMLOX as well. So, and this is the result that corresponds to the result you get in OPUS. You have the average availability over 10 years or what it is. This is the average availability over the time period. So there is no time dimension anymore here. And you have this lower percentile as well here, the average lower percentile. And this goes for almost all results in SIMLOX. You have the time result and you have the total result. So you can toggle between them, as we will see in the demonstration and when we are going into the tool. Some result categories, or before we leave this, was it possible to understand this in a good way? Because this is, according to my experience, this is one of the hardest things for people who are not used to SIMLOX and simulations to understand this kind of results and what it's really representing. So if you feel that this was a bit confusing, it's okay. But we will look at some real diagrams in a while, so we will get back to discuss this. Result categories from simulations. We have, of course, the mission results, very important, key results from the simulation to understand the mission success. What is the performance on the requested mission profile? We have the system results, so what is the performance of the systems? That was the colorful diagram we watched previously to see what does the system do all the time. We have stock results that can display the performance of the spare part stock over time. And we have performance on individual spare parts. This is a result that is toggled off by default because it generates a lot of information. Imagine that they have a system with 500 items and you will collect results for each item for each period in time. It gets it's possible, but it generates enormous quantity of data, so it slows down the simulation. And then you also have the performance of maintenance resources. Okay, are you ready to look into the tool? So, could you tell if we are in OPUS 10 or in SIMLOX now? There's a little, you can't tell because you don't see the upper part of the program, but it's a little small blue dot up here that says SIMLOX. Otherwise, it's exactly the same user interface. So, it's not really a big step to go from OPUS 10 to SIMLOX here, because you recognize the views, you recognize the tables, and everything. So switching between the two programs is very easy. I can switch off to show, because there are some tables and columns that are applicable only for OPUS 10 when you optimize, and some are applicable only for SIMLOX. So in order to keep it more clean, I toggle off this show OPUS 10 column. So now we only see the table columns and tables that are relevant for SIMLOX only, or both. So to reiterate, to refresh your memory a little bit from what we did yesterday, we have modeled the product breakdown, and the product variant, and product realization. All this is also applicable in SIMLOX, the same product variant. When it comes to hardware, same thing, items, item structure, component groups, failures, repair policy, preventive maintenance, all this that we did yesterday, consumables, etc. So that is same information that we had yesterday and we continue to work on. Here in the section of operations, we have now two more tables, mission type and operational profile. No, three more tables, mission type, operational profile, and operations. So remember, yesterday we defined our system, we defined our operational profile with 525 hours per year, and the system deployment for the different bases. But now we have a table called mission type, which exactly allows us to define the smallest building block of defining our operational contact profile. It is the mission type. And there are a lot of properties you could set for the mission. You remember I said we had how many numbers of the nominal number of systems we need to kick off the missions, and then how many systems that are required to perform, to stay on the mission. Then the mission duration, and mission success point, which is by default 100% of the mission. You could also assign a distribution to the mission duration that says that the mission is not fixed length, but it follows a normal distribution or exponential distribution or anything. So this is also one thing that is really interesting when you come into the simulation world and you play the scenario based on random draw, because now we can use statistical distributions to sample from when we are simulating. So the mission could sometimes be long, sometimes short, sometimes it depends on the distribution. When you are working in deterministic model, we always take the average value of the distribution. So you will get the same value all the time. But now we can sample, and this is in many aspects in SIMLOX, you can use distributions for values, for task, repair time, etc. So it's very convenient. We also have some possibility to set mission out time fraction and return fraction. You could say, for example, that it takes some time to get to the mission area, then you conduct the mission, and then you need some time to get back from the mission area. This could be modeled in this aspect. We talked about fixed mission patterns, continuous and extendable. We could set a certain priority for the mission. If we have many different missions, we could, and there's a competition for systems in order to achieve, we can rank the missions in a priority way to say that, okay, if we have to choose between mission 1 and 2, the mission with highest priority goes. We could adjust failure rate for certain missions, and a lot more other properties. So you see the table is very long, a lot of optional functionality that you can use for defining your missions. In this case, I have defined mission 1 requiring 12 systems, but it's okay to do it with 1. And that's a bit odd, I think, but I will explain why I have done like this. And the mission 2 is 4 systems, but it's okay to do it with 1 as well. And the reason I have put it like this is because we want to compare the result from OPUS 10. And OPUS 10 is always assuming that all systems operate this time. If we set the utilization profile in OPUS 10 to 525 hours per year, this is assumed to be used per system. Now this is something to watch out for when you go into SIMLOX. You don't have to model it like this in SIMLOX, but from a teaching point of view and to compare results from OPUS and SIMLOX, this corresponds to the usage in OPUS. So this is something to be careful with, because sometimes users say, I don't understand. The result from OPUS 10 is not at all, the result in SIMLOX is not at all as the expected availability in OPUS. There must be something wrong. But always first question is, are you sure that you're using the systems in the same way as assumed in OPUS 10? And now I have a mission profile. It's more difficult to see how many hours the system is performing. So in order to calibrate the results, we must make sure that the systems are used in the same way. But it's not a requirement. It's just for this purpose here, I put it like that. So, but the tricky part here is not really to define the missions. We need to define our operating profile. And we have a special view for that. That's called here, the profile view, or here you can go, which allows you to more easily see if the profile corresponds to what you imagine, because you build it up recursively. So what I mean by that is that a profile, let's take this one, consists of building blocks, where the smallest building block is the mission. So in this case, I have defined my mission number 2, 4 systems for the base. This is here, mission 2. Then I started by building up a mission week. It says, okay, a week at the base consists of 4 missions spread out evenly over a period of 120 hours. And that corresponds to Monday to Friday, because we don't want to work on the weekend. So this is not really a wartime scenario or something like that, but it's more peacetime scenario, you could say. So if I put 6 here, no, wrong column. I get 6 missions distributed over 120 hours. If I get 10 here, 10 missions over the same period in time. If I want to extend this also over the week, I put 168, I get the missions spread out over 168 hours. So I play with number of missions that I want to conduct and during which time period I want to conduct these missions. I also have a starting time here. So I can say that, okay, we are starting 8 o'clock on Monday, so everything is moved to start not at time 0 but time 8, etc. But that is maybe of more detailed character. So I have my week base, and then I have also then said, okay, I want to define a year directly. And a year consists of 52 weeks. So I have, in the same way as I used the mission, 4 missions during 120 hours, when building up the year, I have 52 week profiles during 8,760 hours, which is the number of hours per year. And I get this profile then. So I can see each week, 4 missions, 4 missions, 4 missions. And this is something I can build up this exactly how I want. I can choose to define a day, and I can combine different weeks into 1 year. I can different days in 1 week, etc. So this is just an example. There is no rule exactly. It is you build up the profile exactly what fits you the best. But the good advice is to create not maybe one profile which is very complex, but use building blocks, because that allows you to modify more easily, to say, okay, no, I want to reuse these building blocks for a new profile, but in a slightly different way.
And some missions can happen in different locations.
Yes, but in this case, we are just working on the profile. We will assign the profile to different locations later. So here is only building up how the mission profile or the operational profile looks like. We don't know yet where we're going to assign it. Here we can see that we have already assigned it because it's shown here, but this information does not contain anything about where it is going to take place.
And it may need some relationship with some support resources.
Yes.
In that column, we cannot find any information about the relationship, the mission with the support resources.
No, that's true, because here we are only defining the operations.
Operation itself.
Only operations. What can happen during operations is that failure occur or preventive maintenance are triggered, and that is then calling for resources.
You will describe in other sections.
Yes, exactly.
레이저 포인트.
Ah, okay, I have here too.
아,
Thanks. Anyway.
제가 잠깐 껴야 될 것 같아요. 이게 중간에 막 느닷없이 시뮬레이션이 나오니까 처음 보시는데 헷갈릴 것 같아서 제가 껴둘게요. 죄송하지만. I think many people don't understand about the SIMLOX environment, only OPUS 10. So we need to, from the beginning, explain OPUS 10 optimization, and then getting us some information too into the SIMLOX, and then making us some mission and profile next step.
Yeah, we come
Outcome,
to... Yeah, absolutely.
제가 잠깐 설명을 드릴게요. 원민입니다.
Yeah.
So, you have a rage? Yeah. Okay. 아까 저 요네스가 여기 뭐 심독스가 이렇게 아이콘을 잠깐 보여드렸죠. 그 이유가 똑같아요. 환경이 오퍼스트하고. 그러다 보니까 이제 이게 지금 심독스라는 환경인데, 예, 그러다 보니까 헷갈려 할 수도 있다 이제 이런 얘기를 했고요. 그 오퍼스에서 우리가 오퍼스10 가지고 할 수 있는 게 뭐냐면 최적의 솔루션을 찾는 거였거든요. 어제 목적이 그거였죠. 뭐 가용도가 됐건 스페어가 됐건 최적의 솔루션을 찾았으면 그 찾아진 솔루션을 가지고 이쪽으로 끌고 와야 돼요. 그래야 될 거 아니에요? 그래야지 우리가 시뮬레이션을 하는 거지.
환경이 똑같으면 SIMLOX 갖고 어떻게 OPUS10에서 하든가 할 수도 있어요.
차이가 요거 하나 있습니다. 오퍼레이셔널 프로파일만 여기서 지정을 하는 겁니다. 심록에서는. 그래서 요거만 틀려요.
여기서 옵티미제이션이 어제
그래서-
했던 것들.
안 되죠. 이건 시뮬레이션이지. 네. 그래서 오퍼스10에서 최적의 솔루션을 찾았습니다. 최적 결과를 이쪽으로 가져와요. 근데 이 과정을 생략을 한 거예요, 지금. 설명할 때. 그래서 그 가져온 결과를 가지고 이제 심동에서는 시뮬레이션을 하는 거니까 이런 미션, 그 다음에 미션들 모아가지고 OP를 만들어가지고 시뮬레이션을 해야 되거든요, 지금. 그런 환경을 지금 설명하고 있는 거고요. 자, 그래서 오퍼스10부터 다시 시작하라고 그랬어요. 오퍼스10에서 최적화 결과들을 어떻게 여기 가져왔는지. 예를 들어서 스페어라 그러면 여기 있어요. 그래서 스페어를 이리 가져와서 그 최적화된 스페어 개수 가지고 우리가 생각하고 있는 오퍼레이셔널 프로파일 동안 해석을 하면 우리가 만들어낸 최적 결과가 시뮬레이션하고 어떻게 매치가 되는지 그걸 보자라는 거거든요, 지금 심록스는. 그래서 스페어가 5개 산출됐네? 그럼 우리가 원하는 대로 5개의 스페어를 가지고 90%의 가용도를 10년 동안 만족할 수 있을까? 이런 걸 보자라는 거거든요, 지금 얘기는. 그래서 그 내용을 다시 처음부터 다시 이렇게 오퍼스10에서 이렇게 가져와서 그렇게 좀 설명할 수 있도록 하겠습니다.
아까 들었던 거는 우리가 시뮬레이션을 하려면 미션뿐만 아니라 또 미션이 다른 지역에서도 발생할 수 있지 않냐. 그러면 로케이션에 관한 정보는 넣지 않느냐. 또 하나 나중에 우리가 리포트할 때 이런 미션과 서포트 리소스의 관계에 어떻게 서플라이 하거나 이런 것들이 같이 들어가야 시뮬레이션이 되지 않냐고 물어봤어요.
그런 건 다
그런
가능합니다.
거는
네.
나중에 다시 또 이렇게 디파인을 할 거다. 여기는 미션만 정의를 하고 있는 중이다. 그렇게 아까 얘기한 거죠.
예, 그런 미션 조합에서
미션만
말씀하신
지금은 얘기하고 있고 아까 그런 릴레이션십 로케이션 같은 것들은 결국 로케이션이 10개면 이런 걸 10개 할 거다. 뭐 이런 얘기를 한 것 같아요.
예, 그렇게 말씀하신 오퍼레이셔널 프로파일은 여기서 지정이 가능합니다. 네. 그래서 acquisition from the OPUS10 and then getting us some optimal information, put in the SIMLOX,
Yes.
and then, making us some simulation.
I will come to that.
Sure.
Sure.
Thank you.
Thank you. So, before we conclude the operational profile discussion here, we had a very deterministic way of determining how the missions are outlined in time. And you can see here that we have some kind of initiation type, which says scheduled. But maybe we don't know exactly when the missions are going to take place. So you can also say that we have random initiation type to say, in this time period, we will have, of 120 hours, we will have 4 missions. But at random point in time, we don't know exactly when they're going to happen. So you see the difference here from scheduled, then it's fixed time the missions will occur, to random, to say we have somewhere in here. And when the simulation plays, we will see when the mission will occur. And the same way, now we have distributed the missions equidistantly between the missions. You could also here say that the missions will occur, maybe 2 missions will occur very close to each other, or some will occur pretty far from each other. So you can play a bit with these factors as well here. And we have something also called deferment time, which means that we have some slack. So let's say we have 1 hour deferment time. That means if the systems are not ready at the point in time where the mission is scheduled to start, we can wait 1 hour to see if the mission, if the system becomes available, then we can start a little late on the mission. It's okay. With no deferment time, if systems are not available at the start of the mission is aborted. So some things like that. So we have defined the missions, and we have defined the operational profile, and in the table operations, we can see here the operational profile was built up, and we had this year annual profile, which describes 1 year. So we have 1 year at the base, and we have also one profile that is year at the main base. And in this table then, I assign the base, you know, the alpha, beta, and gamma base, and the main base, to corresponding profiles. So say, these vehicles should operate according to main profile. And these vehicles will operate according to base profile. And now we are ready to start the simulation. Yes?
About the mission type, I don't see there factors about the times or the minimum number of systems required. Is there any way to set the intensity of the mission? Because I think some missions usually more tough or harder so that it can cause more aging or damage to the system.
Yes.
So is there any way to set the intensity of the mission as certain values?
Yeah, you could do it in different ways. You could apply, as I said, this mission failure rate factor that says that, okay, for this mission, it is 1.5, it's 50% higher strain on the components, which makes them more inclined to fail. So this is one thing to do. Also, you have a lot of variety here. If I show you the optional tables for mission details. So you have mission reliability, which allows you to set different reliability factors depending on missions. Mission dependence, missions that are dependent on each other to work, etc. So this is what we showed you. What I showed you here is the really simplest way of building up the missions. But SIMLOX offers really complicated structures and combinations and formations in order to define very complex mission profiles. Also, what you asked for with different strain on the system and which requires extra. You can also define which components that are critical for some missions but not critical for other missions, etc. So you could spend easily 2 days in different kind of mission complex modeling in SIMLOX. Any other question? So, before we start the simulation, we will go to the control table here, because that contains some important information. Here I can set the simulation period. I need also to feed the simulation with a random seed number. This is from a simulation tool perspective. You have to give a number to kick off the simulation so that it will. And if you replicate this number, you can always come back to the same result. But let's not think too much about this. Number of replications by default is 1. And we will start the first simulation of only 1 replication. Then we also have another interesting parameter that's called result collection interval, because SIMLOX is calculating not only the average result over many replications, but also over time periods. We cannot collect information for each hour. That would be too much information, and it would not give us any particular value, certainly not if we're looking at a longer time horizon. So the default is 24 hours. That means that SIMLOX calculates the results in groups of 24 hours and presents it to us. But we can change that. We could set 1 hour, we could set 1 month. It depends on the granularity of the result. But let's do a simulation now. And we look at the mission results. This is the result on the operating profile. But it's also, we can start to look at one base. Let's take the main base, for example. And I think that was only mission 1 at the main base. So the requested profile was like this. I can zoom in a little bit so that you see. And the result is like this. The red is mission time that we did not fulfill. So we can see we start here. We start with all 12 systems working, but we will start to accumulate failures. So here we only have half of the systems in operational conditions. Then some systems will come back, but we will also decrease. So this shows us the result according to the mission profile.
It's not 12, right? It's just showing the number of systems that are used in utilization on average. It's not,
Yes, but it's also in 25 over 24 hours.
Yeah.
You are not using the systems all the time during the 24 hours. If we look at the mission time, we can see that we have 100% mission success. And that's what we defined. We said that the mission was okay to run with, start with 12 systems, but it's okay to run the mission with 1 system as well. And we have probably a lot of systems there. We had 12 systems on the base. But if we look at the system time, we are losing system time. So difference between mission time and system time. If we look at another base which has fewer fewer vehicles, we see the same thing here. We are able to conduct the missions with only 1 system, but we are gradually losing some systems over the course of 1 year. But here, I must look a bit in my notes. This is 1 year, 1 replication. We need to augment this to 100 replications to see what the result will be from a more statistically correct perspective. And then we can see here that, okay, we are stabilizing around 70% mission fulfilled system times on the mission. And when it comes to mission time, we are losing a little bit up here, but not too much. But we have cases where we are not able to fulfill the missions. So now we have run the scenario 100 times. So if we look then at the system, we can see what's happening with the systems. Well, they are on mission, fully capable, but they are also in a ready state and unavailable. So the total fleet of 24 systems, we have about 17 systems that are operational and 7 systems that are unavailable. And why are they unavailable? We are awaiting items, and therefore I forgot something. We don't have any spare parts in this model. So let's go back to OPUS 10 and make the calculation. You remember the curve in OPUS 10? Spare parts. What I want to do now, I want to use the result from OPUS 10 in the simulation. And what I talked about, how can we verify the result from OPUS 10 into the simulation world. And to make things easy, I will see what point I needed for 90%. This is 0.24. I will, let me see, I clean this table, and I will do right click here and say insert stock allocation. I insert this into my case. So now I have the information about the stock here and about the reorder policy. So now I can open the case in SIMLOX, the same file, but different program. And I see here that I have my stock allocation. And if I go to program control here, I can see that we have a point that says allocation point identifier. So this allows me to set 0.24 here. We have 100 replications. And let's run the simulation again, but with spare part stock. And if you now look at the system states, we see that unavailability is much lower. We can toggle between the case. This was without spare parts. Now we have spare parts. Much better situation. And when we look at the system, requested system time on mission, we also see much better. And that's maybe not rocket science. We are performing better with spare parts than without spare parts. But this shows you how you integrate the result from OPUS 10 into SIMLOX. And now I can really, now we can see if we have correspondence between the two programs. So in OPUS, we had 90% availability. This stock should give us 90% availability. And if I verify here total and in percentage, let's look at availability. Oh, we have much better availability, in fact, in the simulating. 94.8. But on the other hand, the OPUS scenario was calculated over 10 years, and here we're only looking at 1 year. That means that we could have some positive effects from the beginning of the scenario where we don't have any failures. So if we instead run the case with 10 years horizon, I have updated the maintenance profile or the operational profile not only for 1 year but for 10 years. So we have the yearly profile and I prolong it over 10 years. And I also set the simulation period to 10 times for 10 years. And the same allocation point identifier. And we run the simulation here. We see, if we look at the total value and availability, 91.3. That is close enough, I think, to 90.5, because we will always have some changes you will never get the exact same result from a deterministic model in a simulation model, but this is close enough to convince me that OPUS was right here in giving that the average availability over time will be 90%, and this is what we get in SIMLOX. And that is also because I made sure that the utilization of the system would be equal between the two, both the operational profile and the OPUS 10 utilization. And I think in many cases, this is not how you model. You have some other variations when you are modeling an operational profile than you have when you are calculating with the average utilization. But this is to show you that when the utilization is corresponding between the two models, we get the same result. There must be some questions, I guess.
Do you apply this to real developers, maybe, or
I did not understand. Could you repeat, please?
yes, you apply this approach to real field developers, maybe for Army, because I think in the real world, the operational profile is more complicated.
Absolutely.
Yes. So it's very hard to describe the situation in operational profile.
Mhm.
So I ask you, do you have any experience to apply this system to the real world?
Yes.
So do you have any cases?
We have a very simple operational profile
Yes,
in
then
this
it's
program.
education, yes.
But as I showed you, here, for example, is a very complex operational profile.
Yeah, yeah.
Do you remember the profile that Oscar showed you from the deployed operations planning? We had different that was solved by heuristic optimization with EVO. That was also an operational profile consisting of 6 different mission types with different requirements. So I think you can build how complicated mission scenarios that you need. And we have also customers that have verified the results from SIMLOX. I think it was the UK MOD that have conducted follow-up, revisited the model after the real world to see if the simulation results corresponded to what they experienced in the real world, and they actually concluded in that study that this was very close between the simulation result and the real world as well. So we have, I think SIMLOX is widely used among our customers in order to describe their operational, to study operational effectiveness.
I think it's very powerful when you apply this in the real world because it has a feedback system. First, you optimize the program and you test it in SIMLOX, and you can change the so-called resources in local stand, and you can find another result. Okay, that's good.
Yes,
It's a very powerful system, I think.
indeed.
But the problem is how we can apply this system precisely in the real world. Because to make an operational file is very difficult, I say. It needs some professional support.
Yeah, it could do. Absolutely.
But there it is important to remember that this is a strategic tool, so you're not necessarily looking for exact results. You want to know more so you can get better decisions.
Yes.
And then you can improve and get even better accuracy and so on. And I think it's quite common that when you've made your first analysis, you present to your experts, operational experts, and they can evaluate, and then you discuss what assumptions were made, how can we improve something on the modeling and so on. So it's not a one simulation, now we have the answer, it's iterative process all the time. Get better at the accuracy. Yeah.
Thank you.
So, was there anyone who noticed when we extended this scenario into 10 years? If we look here at the system states, we get a quite interesting phenomenon occurring regularly. These spikes,
Yeah.
what could that be? Why are we regularly having a dip in system availability? We can also see, I think, if that is mirrored in the... you can see here the spike, we are actually losing mission time regularly here as well. From an operational perspective, it's maybe easier if we look at one base. Preventive maintenance. I'm happy that you say that. It's a good suggestion. Because you remember that we had in the model, we have our preventive maintenance, which occurs annually for the variant each year.
Yeah.
This looks like something that happens
Yes.
each year.
Yes.
And then you have a much bigger, broader period of unavailability here.
Overall.
We have the overhaul for the engine, which happens every 500 operating hour. Interesting. It's not as predictable because we don't know how much each system individual is being operated. But we know that every system needs to go out once a year.
Every 5 years.
So the mission profile translates, so we can assume that after 500 hours, that is after 5 years, on the average, the system individual has been operated for 500 hours. But I'm not sure that we want, that this is something that occurs, in reality, that you take out all your systems for annual overhaul at the same time. We would like to have that more spread out so that we always maintain an operational capability. And maybe that is also more closer to reality because the systems have been in operation different time. Especially if we have a phased-in scenario where systems have been deployed gradually. And in order to address this, we can, since we are now in the time dimension, we can now add age to our systems. I will close down some of the previous ones. So if we have our fleet of systems, which are 24 systems, I will add 2 more sections of information here. The time distribution and something called initial state. And in the initial state table, I define a variable that says that is following a rectangular distribution that will draw a random number between 0 and 1 year. And then I will assign this to my systems here in a table called system deploy my initial state. That tells me that for each 12 system at the main base, I will apply this age factor that will say for each system, draw a random number between 0 and 8,760 and give this age to the system. And the same thing for each base. So that will mean that when we start the scenario, each system will have different age when it comes to the calendar-based overhaul. So that means that they will reach the limit at different points in time. They have a clock ticking, and in the first case, everyone started from the clock ticking at 0. That means that everyone will reach 1 year at the same time, and we get the dip in the operational capability. But now, when we start the scenario, the initial state of the clock will be different for each system, which means they will reach the 1 year deadline at different points in time. Some might be very close, so that they will go out for PM already early in the simulation, and some might be longer away. So if we apply this to our simulation, we get another behavior. So if you compare now without the initial state, with the initial state, you see much more smoother availability here. If we look, for example, at unavailability, we can see active preventive maintenance with the initial state and active preventive maintenance without. You have these spikes, the blue color here. So this is a feature that you can use in order to get a more realistic view, because it's not realistic that you plan calendar maintenance for every system in your fleet at the same time, because then you are without capability.
혹시 이해가시죠? 제가 설명을 할까요? 아니면? 시뮬레이션하는 첫 번째 목적은 이걸 보기 위함이고, 이걸 보고서 끝나면 안 되죠. 예를 들어서 지금 웨이팅 타임이 스파이크가 막 생겨버렸네. 그럼 어떻게 해결해야 되죠? 저걸? 어떻게 해결하는 게 좋겠어요, 혹시? 이 친구가 얘기한 거 말고, 이니셜 스테이트 말고 다른 방법이 혹시 있을까요? 혹시 그냥 경험적으로 만약에 저런 문제가 생겼어요. 우리 어떻게 해결해야 돼요? 저게 평평하면 좋은 거 아니에요? 우리가 솔루션을 내서. 아니 뭐 정답은 여러 개입니다. 좋은 방법이 혹시 없어요? 경험적으로. 뭐 예를 들어서 간단하게
속도를 더 갖고 가든지,
뭐 그럴 수도 있겠고,
트랜스포테이션 속도를 높이든지,
아니 뭐
행정 시간 줄이든지,
일단 좋은 답이 뭐예요? 스팸 모자라네. 몇 개 더 갖다 놔.
이벤트를
네. 그럴 수도 있는 거고, 미션을 조금 더 정확하게 한다든가, 아니면 이니셜 스테이트에 대한 가정을 조금 더 현실화한다든가. 아무튼 시뮬레이션 하는 목적이 이제 이 결과를 보고 우리가 어떻게 하면 저런 것들을 줄여내야 될지 실제로 그걸 하자라는 겁니다. 지금 현재 시뮬레이션 하는 것들은. 그래서 그 지금 유네스가 보여준 게 유니폼 디스트리뷰션이잖아요. 1년짜리 유니폼한 랜덤 넘버를 끄집어내서 상황에다 계속 동일하게 유니폼 랜덤 넘버를 적용해서 시뮬레이션 할 때 저렇게 나왔고, 만약에 그럼 이걸 현실화해가지고 이니셜 스테이트에 대한 가정을 조금 더 현실적으로 집어넣으면 어떻게 되냐면 우리가 마구잡이로 했던 시뮬레이션하고 조금 더 다른 결과들이 나온다는 얘기죠. 물론 전체적인 경향은 비슷하겠죠. 그래서 그런 것들을 이제 시뮬레이션을 반복을 해가면서 우리가 현실화된 모델을 하나 둘씩 추가를 했을 때 진짜로 어떻게 되는지 결국 이제 그런 걸 보자라는 게 이 시뮬레이션의 목적입니다, 사실. 오케이?
Yeah. Thanks, John. And it's also don't mistrust if you feel that this is quite complicated things, because you learned it. Typically, you go a 3-day basic course in SIMLOX, and then you get a 3-day advanced extension course in order to learn how to model this. So if you don't get everything right now, don't despair. It's more for showing you the capabilities of what you can, how you can use the tools. So, if we have one more thing before we are ready for lunch break. But I want to see here, we can see that we have this spike on awaiting items. And this would be quite interesting to know why do we have this spike for items. There is probably a bottleneck somewhere. And then we have some other results here. We have stock total results that can show us things about back orders. So I will remove this first case now. That says, okay, we have back orders here. Then that means unsatisfied demand. What is causing this unsatisfied demand? We don't know, because here's on the average all stock, all items. So I would like to dig deeper into here to find out exactly what item is the bottleneck here. And by doing that, I need to switch on something called track for my items, because by default, SIMLOX is not saving result on all items, because that is not meaningful if you don't need it, and it will take a lot of simulation time to do that. But if you need item results, you can switch on collect item results, track, and you will get information about each item's performance. Typically what you want to do as well is to maybe large the result collection interval so that you don't sample every 24 hours during 10 years. We just do every month now. That will speed up the simulation. So we see that it's a bit hard, it is not as fine, the granularity, but still we have this spike of back orders. And we want to know exactly what type of item that is. So now I can go to item results. I can see over all items, we have the current stock level, how many items that are in resupply, that means in repair or transport or something, and then how many back orders we have. And here we can see, we can look at, for example, what is the situation at the central store. We have this back order spike at the central store. It's propagated to the different locations. And do we see that this spike corresponds to some activity? We saw before that we had this maintenance, preventive maintenance coming somewhere at about 50,000 hours. So coming back here, we want to look at the total result. And here we can switch off for the back orders. You can see per item, and we see that we have at the central depot, we have quite the stock situation at the central depot. And if we want to look at only on the back orders, I filter that out. We see engine, and then followed by the VPU, etc. So it is very likely that the spike is that because we have a lot of systems coming in for the engine overhaul after 500 operating hours, that sending away engines to the central depot, but we don't have that many engines in spare parts, because engine is expensive, big spare parts, and typically you don't keep so many of them at extra because they are expensive. So when this preventive maintenance occurs, there will be some downtime induced because we wait for the engine to come back. We have to wait for the engine to be maintained because we don't have a spare engine to replace the maintained engine in. So this is an insight from the simulation that is very clear here. We get downtime because we don't have enough engines, and we must find maybe a way to speed up the maintenance of the engines, or maybe if we have the money, invest in 1 or 2 spare engines. What would that make, etc. So this is a very good example of how the simulation lets you identify a problem area. And once you have identified the problem area, you can understand what kind of actions do we need to take in order to avoid this problem. And then the last thing I wanted to show you before the lunch is that another thing that is important to study in SIMLOX is the use of resources, because resources is also something that could be a bottleneck in order to use the performance. When we look here at the system results and the unavailability, we have awaiting resources as one of the reasons for not performing. But we can't really see that. It's very feeble somewhere here. It's not, you see, 0.05% of the cases we are down because we are awaiting resources. So it's not significant. But let's try to use the resources. Let's say that the resources is required to perform the preventive maintenance as well. First, we only had this resource to replace a primary item. That is a quick activity, which is not requiring the resources for a very long time. But let's say that in reality, we require the resource for all this overhaul activity. And we have also put out the resource not only on the basis, but also on the central depot and the regional, or the central depot first, because that's where the engine overhaul takes place. And also another thing, let's say that the resource is not used 24 hours, 24/7, only used, work 8 hours per day. So we need to understand that the resource is used only 33% of the time. So if we make simulation now, and go back to system states, we see that we have still unavailable for some reasons, but we can now see that the unavailability is to a much greater extent also depending on the resource shortage. We are waiting resources. And looking at the resource results, we can see that the resources we have in total 7 technicians. We will select the technician here. Okay, 5 technicians do we have in total. It could, the technician can be working. It could also be available for not working, but still available. And it can be closed and awaiting. Closed means that he has gone home because the workday is over. So he's needed, but he's not working. So we have to wait until tomorrow, until he comes back at work, and then continue the work. So this is the extra demand. You could say that this is the resource back order, awaited. So we see that we induce downtime for our systems because we are waiting for spare parts, but also we are waiting for resources in order to conduct the maintenance. And we can also get a good idea here of the total, the average states for the resources. In the first case, we had only 4 resources. In the second case, we have 5 resources. But on the average, 1 resource is at home. And on the average, a little more than 1 resource is awaited. So here you can play with the number of resources to see exactly how many resources are required for achieving your goals. And this is also, if you remember, I talked about Opus Evo that optimizes input data. You could use Opus Evo to optimize what is the best number of resources and allocations to meet a certain mission profile. So now I think we have had 2 hours almost for this. I think you must be quite exhausted after seeing all these diagrams and things. And I think I reiterate, don't be afraid if you don't understand exactly how you accommodate all this. The purpose here is to show you the impact of dynamic changes and also what are the possibilities with the simulation to identify not only mission success and system availability, but also bottlenecks for various maintenance resources like spare parts, like technicians, etc. And that this gives you the possibility to foresee possible bottlenecks and what you can do about it in order to address the right thing when you are dimensioning your support organization. Any questions? Yes.
Mr. Ernest, I have a question about the graph that you presented before. The 100,000 hours for the number of spare parts or resources. If I want to search for the spare parts status or resources at the specific points, I mean, for example, it could be 30 years or 4 years. Can I search it and the list of the spare parts or resources?
At a specific point in time?
Yeah, that's right.
You mean? So if we are looking
I don't know the exact list of the spare parts or resources.
You get a lot of results from SIMLOX as well. This is visual results, but you have the report as well here with a lot of both tables and diagrams. So I can generate this report and I can find resource utilization both in table format over each time period, but also on the whole simulation. You get total all resources over all stations, but you can also get, for example, results for specific resources and specific stations. So here you have for all technicians over all bases and how much they are used, how much they are awaited, how much they are available, etc. Is it that what you mean?
Yeah, that's right.
And you can get that for items as well, for spare parts as well. But as you see, simulating over 10 years, and if you sample the result every 24 hours or every month, you get huge amount of results. So this is like big data mining if you are going to in the different the details of the simulation. And that is something that we have been working a lot with recently, improving the performance of big simulation results. So we are much, much faster now than we were for a couple of years ago, because we have really we have had customers with very demanding cases who have asked for the possibility to collect results on a very granular level. So we have had to increase performance, and I think that, I don't know the magnitude, but significantly. Any other question? Okay, John, time to wrap up before lunch.
혹시 뭐 저한테 질문하시면 제일 많이 들어오는 질문 세 가지만 간단하게 말씀드릴게요. 아까 릴리피케이션에 대해서 제 질문이 많이 나왔고, 시뮬레이션 한번 10년짜리 한번 할까요? 그 다음에 시뮬레이션의 타임 스텝, 아까 하루 단위도 할 수도 있고, 기분 나쁘면 1시간 단위도 할 수 있습니다. 지금 요네스가 얘기했죠. 방대한 양의 결과들이 나옵니다. 지금 보셨지만 이걸 다 자료를 다시 리뷰하는 것도 사실 어려운 얘기죠. 아무튼 결과들을 뽑아줍니다. 그 다음에 두 번째로 많이 들어오는 질문이 랜덤 시드에 대해서 이렇게 많이 들어오는데, 랜덤 시드를 똑같이 놓고 시뮬레이션이 계속 반복하면 결과는 어떻게 된다? 당연히 계속 같지. 그래서 시뮬레이션 할 때마다 랜덤 시드는 조금씩 바꿔주셔야 됩니다. 똑같이 주고 계속 하면 안 돼요. 그거 질문 많이 들어오는 거죠. 그 다음에 이게 시뮬레이션이 의미가 있나? 이런 질문 하시는 분들이 계세요. 우리가 이성적으로 리저너블하게 동전 던지기 해서 앞면, 뒷면 2분의 1이 나오는 건 당연히 알고 있습니다. 그죠? 근데 그러한 과정을 우리가 계속 반복 수행을 하면서 2분의 1이 나온다는 걸 입증하는 거죠, 그건. 우리가 실제로 하는 것들. 그래서 리저너블하고 우리의 순수한 이성을 가지고 어떤 값이 나올 거라는 걸 얘기할 수 있으면 가장 좋은데, 2분의 1 것이라는 거는 알고 있지만 이걸 우리가 입증하는 문제는 또 다른 문제라는 겁니다. 지금 이 복잡한 시나리오에서 저렇게 될 것이다 라는 거는 우리가 대충 경험적으로 알고 있는데, 실제로 그럴까? 입증 한번 해봐. 이건 다른 문제입니다. 근데 입증할 수 있는 방법이 뭐 여러 가지가 있겠죠. 방대한 양의 자료를 몇 달씩 밤을 새가면서 검토를 해서 입증하는 것도 좋은 방법이에요. 하지만 간략화된 모델을 통해 가지고 이렇게 시뮬레이션을 통해서 입증하는 것도 상당히 중요한 방법 중에 하나다, 이렇게 생각을 하시면 되고, 시뮬레이션을 왜 하냐 할 때 제가 주로 답했던 게 뭐냐면 아까 같은 문제예요. 아니 왜 어베일러빌리티가 갑자기 이렇게 줄어들지? 그것도 주기적으로 나오지? 이런 문제들에 대해서 언제 어떤 놈이 어디서 어떤 문제가 생기는지 이것들을 또 시뮬레이션을 통해서도 파악을 할 수가 있다는 장점이 있죠. 아까는 뭐 답이 스페어였죠. 스페어가 모자라서 이렇게 계속 이런 일이 발생이 되는데, 이랬을 때 우리는 어떻게 대책을 세워야 될까? 뭐 이런 것도 하나의 방법이 되는 거죠. 그래서 그런 차원에서 이제 시뮬레이션을 많이 해야 되는데, 여기 계신 분들을 무시하는 게 아니라 우리 군수에서 이런 기법들을 적용한 적이 거의 없어요, 사실. 제가 알기로는. 그래서 약간 낯설 수도 있고, 이렇게 빨리 감각적으로 우리가 이해를 한다는 것도 좀 어려운 문제도 있고요. 만약에 몬테칼로 시뮬레이션만 얘기하는 것도 아까 이 친구 얘기했었죠. 한 3일 동안 얘기해야 됩니다. 아니 왜 유니폼 넣은 거야? 나는 전기공부 쓰고 싶은데, 나는 지수루프 쓰고 싶은데, 이럴 수도 있을 거 아니에요. 왜 우리는 유니폼 써야 되지? 그게 타당한가? 뭐 이런 것부터 시작하면 사실은 할 얘기가 너무 많습니다. 그런 것들. 그래서 그런 것들을 빼고 오늘 오전에 한 시뮬레이션에 대해서 요약을 정리하자면, 어떤 놈이 언제 무슨 문제를 일으키는지, 그러면 그걸 우리가 대책을 어떻게 세워야 될지, 군수 공학 입장에서 이것들이 이제 시뮬레이션 통해서 한번 알아보자라는 게 심독수의 목적이고, 그 다음에 염려가 돼서 소프트웨어 사용하고 뭐 이런 메뉴를 쓰고 뭐 이런 것들에 대해서 제가 아마 따로 교육을 해요. 다음 달도 하고 이번 달도 하고. 그래서 그런 시간에 교육을 신청을 하셔가지고 오시면 도움이 될 거라고 생각이 됩니다. 일단 점심 식사를 하시고 어제처럼 한 1시 10분 정도 시작하면 될까요? 1시 10분. 네. 그래서 혹시 뭐 저한테 하실 얘기 있으면 저한테 질문하셔도 직접 하셔도 돼요. 1시 10분에 다시 시작합니다. 1:10 we start the meeting.
1:10.
You said about S-3 policy. Yesterday you said about S-3 policy.
Exactly.
For example, such policy is applied to all the items, or it is differs item by item.
Again, but if it's applied to
Yes, as my